So we've been working with this for a week or two now. So, okay, I've done a couple of recaps on this at the start of the last few lectures. But the main thing to keep in mind is the definition of the Euler function, the Euler totient function, the number of integers less than n that are co-prime to n. It's the size of the multiplicative group of congruence classes. So we're interested in it for that reason. And also, it allows us to simplify exponents, okay, because of Euler's theorem. Euler's theorem tells us that if A is an element of the multiplicative group of congruence classes, then A to the power of phi of n is congruent to 1 modulo n. Okay, so whenever we see large powers of an element, we can, as long as we can break down the exponent with respect to the modulus phi of n, okay, and that will tell us what the power is congruent to modulo n. Okay. We work with examples of that in the tutorial. So on. So we're interested in phi for these reasons, the Euler totient function, and we have a really nice formula for phi based on the prime factorization of the argument n. So if you know the prime factorization of n, that means you know the value of phi of n. Okay, because phi of n is built up as a product using the ingredients from the prime factorization of n. Okay, so n will factor into a product of the powers of primes, and phi of n has the value where you have the same primes raised to the power 1 less than they were. And for each distinct prime appearing here, you've got this extra factor, which is 1 less than the prime. Okay. And so it's a really nice formula, very clear connection between the prime factorization of the argument and not the prime factorization of phi of n, but a nice product formula. Okay. This isn't necessarily a prime factorization for phi of n, because these numbers, these extra factors here in the brackets, won't be prime in general, okay? Because 1 less than a prime in general is an even number, so it's not going to be prime. So there will be further prime factorization to do on this. Okay, we proved this in a couple of stages. The main tool, the main kind of lemma that we used, that the thing that our proof was built on, was this property that the phi was multiplicative. Okay. Phi of a product is the product of the phi's. Okay, that's the general multiplicative property in number theory. When you say multiplicative, you're only talking about when the factors in the product you're applying it to are co-prime. That's all we require for when we use the term multiplicative in number theory. If you use it outside number theory, you're probably talking about this property referring to every possible product A times B, okay, with no restriction of it. But that would be quite a, there wouldn't be many interesting functions that are completely multiplicative in number theory. So if we weaken the requirement, so it only has to work when the factors are co-prime, then that's a lot more interesting. There are a lot more functions that satisfy that restricted type of multiplicative property. Okay. And that was the main tool that allowed us to build a induction proof of the product form. Okay, so where the base case was, I know I'm repeating myself, the base case was looking at the value of phi on the power of a single prime. We proved that with a direct counting, just carefully enumerating the numbers between 1 and p to the a, which are not co-prime to p to the a. And we found that there were p to the a minus 1 of them, all the multiples of p. So you just subtract 2 to get the value of phi. And then the multiplicative nature of phi allowed you to build the induction step, okay, to talk about numbers that were not a power of a single prime, but a power of product of powers of 2 primes instead. So before we continue, what we're going to continue with now is there's a couple of other problems here which I had in this example 5.1, which is further working with phi, working with the product formula, trying to reason about phi. So I was going to do those today, so it's quite a practical class. But any questions before we get started? Anything I could clarify for you about where we're at? Okay. Okay. So let's get started on these. So these are on page 38, just towards the bottom of the page, example 5.1. So the first one, question 1, is prove this equals that if and only if n is odd. Okay? So we want to prove that phi of n is equal to 2 times n if and only if n is odd. And you can relate this, I think, to one of the accumulation lines in the. Sorry, no, there's a phi around this. Phi then is never bigger than n. Sorry. Phi of a prime number is 1 less than the prime number. That's the kind of maximum value phi can have compared with the argument. Sorry. Phi of n is equal to phi 2 times. If and only if n is odd. And so the first thing to notice about this, it's an if and only if. So you've got 2 directions of implication to prove. The equation implies n is odd. And secondly, n is odd implies the equation. So the simplest way to approach this would be to take each direction. So first of all, we could assume n is odd. So if n is an odd number, then that allows us to approach the value of phi at 2 times n in a sensible way. Okay? Because if n is odd, then 2 times n, here we're expressing the argument to phi as a product. 2 times something else, but when there's something else, the n, when that's odd, means that the 2 and n are co-prime. If n is odd, it means 2 does not divide n. So these are co-prime factors. Okay? So that means you can break apart the phi using the multiplicative property. Okay? So this tells us that this is phi of 2 multiplied by phi. Since phi is multiplicative. Whatever it was, lemma 5.5. Recorded there, and clearly the GCD of 2 and n is 1, when n is an odd number. Okay. Well, okay, we don't know what n is, so there's not much further progress we can make with phi of n, but we can make some progress with phi of 2. What is the value of phi of 2? How many integers between 1 and 2 are co-prime to 2? There's only 2 things to test. 1 is certainly co-prime to 2. 2 is not. Greatest common divisor is 2 and 2 is 2. So it's not co-prime to itself. So this is equal to phi of n. Equal to phi of n since phi of 2 is 1, just by direct. Just directly from the definition of phi. Okay. So we certainly get one direction. If n is odd, that means the equation phi of n is equal to phi of 2n is true. Secondly, we want to go the other way. Okay. Now we must prove the other direction. Namely, that the equation is true. That implies n is odd. Phi of n is phi of 2. And there are a few different ways you can prove this. It's kind of hard to prove it directly, just assuming this and then from that deriving over there the n is odd. It seems to fall out easier if you do it by proof by contradiction, or more or less, if you're doing a proof by contradiction, you can also phrase it as proving the contrapositive. Okay? Remember, when you're trying to prove implications, and if you're having difficulty constructing a proof directly, where you assume the left-hand side of the implication and try and derive the right-hand side, very often if you switch to trying to prove it using contradiction or maybe proving the contrapositive, that can often, the proof can often fall out easier. Often when you look at the contrapositive, you're given a few more handholds to get things to build an argument. Okay? So we will prove the contrapositive here. We'll do this by proving the contrapositive, i.e., so we have to say not n is odd implies not the equation. So if n is even, we want that to imply that phi of n is not the same as phi of 2 times. And the reason this might be easier to approach, because this assumption here is very easy to work with. It's very easy to encode and get down on the page the fact that n is even. And in the original statement, when you're trying to prove n is odd, you're kind of trying to prove an absence of something, trying to prove that n does not have a factor of 2. That's maybe a little bit harder to get hold of. Okay? So we're going to assume n is even, and then argue that, although we won't be able to evaluate these values exactly, because we don't actually know what n is, we just know it's some even number, but we'll be able to break them down enough to show that they can't be the same. Okay. So we assume n is even. I.e., it can be written now, if you're saying n is even, normally you'd say, okay, it can be written as 2 times something. But because we're going to talk about the Euler totient function, and we know that that's multiplicative, if we're going to the trouble of factoring 1, 2 out of n, we may as well drag them all out. Okay? So take all the factors of 2 out of n. So n, we know, can be written as 2 to the k times n, where n is odd. So any 2's that there are dividing n, we bring them all out here. Okay. And since we're assuming that n is even, we know that this exponent is at least 1. Okay. Because n is even, it does have a factor of 2. So this exponent on the 2 there must be at least 1. Greater than or equal. You can always write any integer at all as some power of 2 times an odd number, but then you have to allow that the exponent may be 0 for the odd integers. We don't have any factor of 2. But we're assuming n is even, so it has at least 1 factor. So then we can say something about phi of n, which will be phi of 2 to the k times n. We can again use the multiplicative property, because these two factors here, 2 to the k and m, they're coprom, okay? Because m is odd. M is, we've taken all the evenness out of n, put it into this factor here, 2 to the k, so the bit that's left behind is odd. So now when we're looking at this product here, it's a product of coprime factors. So again, you can split it into the product of the 5 values. And like before, similar to before, there's not much I can do with phi of n, because because all I know is n is some odd number. I don't know anything else about it. But 5 to the power k, I can write down exactly. Okay? It's using the product formula. When you've got phi of the power of a prime, remember that was one of the lemmas. This is just the same prime to the power 1 less than it was times p minus 1. Okay? That's the product formula for phi when you just got a power of a single prime. So that was one of the first lemma 5.2, or just talking about the product formula. So this is going to be 2 to the power k minus 1 times 5n. And I won't bother writing down the extra factor 2 minus 1. So it's just a 1. Okay. That's just from the product formula. Okay, so 5n is 2 to the power k minus 1 times 5n. On the other hand, phi of 2 times n, this will be phi of 2 to the k plus 1 times n. Remember n, we're assuming is 2 to the k times n, so if we're considering phi 2 times n, remember we're trying to demonstrate that this equation is false. We're considering phi of 2 times n, so that bumps up the power of 2 by 1, yeah? So it's now 2 to the k plus 1 times n. But again, these are products of co-prime factors. M is odd. It's not divisible by 2, so the greatest common divisor of these two factors is 1. So you can write this as 2 to the k plus 1 times 5. Again, using the product formula, this is 2 to the k times 5. Actually, we're seeing that phi of n is this value, phi of 2 times n is this value, so the value of phi of 2 times n is twice that of the value of phi of n. So actually, phi of 2 times n is equal to twice phi of phi, which is certainly not equal to phi of n. Okay. So when we assumed n is even, that proves the equation is not true. So therefore, contrapositive, we've proved that if the equation is true, if phi of 2n is equal to that, then n must be odd. So what we proved is, we proved here that phi of 2n is equal to phi of n in the case where n is odd, and it's equal to 2 times phi of n in the case where n is even. Maybe I should have phrased the exercise like that. Maybe that's a better phrasing of the exercise. Prove this. So we can very easily understand how the value of phi of 2 times n relates to the value of phi of n. It just depends on whether n is equal or not. Okay. Is that okay? Any questions about that? But it shows you using it shows you the use of those two main tools, two main facts around phi. On the one hand, the product formula for phi, and the fact that phi is multiplicative. Who was that? Okay. So any questions? Okay, let's look at the second question. So the second question is solve phi of n equals 12. Short and sweet. Find all integers such that phi of n equals 12. Or in other words, another way of phrasing it, for which integers n is the order of the multiplicative group of congruence classes equal to 12. Are there any such n for the group of congruence classes of integers under multiplication modulo n is 12 or not? Now, there's a couple of ways you might approach this. You could approach it quite computationally. Here. Start. So remember, I might have showed you this in the tutorials. Sage can plot the that's a bit bigger. Sage can plot the Euler phi function. Here it is. So this is for every integer between 1 and 100. So these are all the values of phi of n for n between 1 and 100. So here's 20. So 12 is about halfway here. So you know there's a few candidates for which phi of n might be equal to 12. Okay. So if any of these dots here are exactly on the line, any phi of n equals 12, there'll be solutions. But once you get on out here a bit, there don't seem to be any more solutions. So we could just compute, say, the first 100 values and just pick out the places where we see 12. The only problem with that is, as you increase the range, it's a little bit unclear about, would there be any more solutions for phi of n equals 12? It was very easy to understand the maximum possible value of the phi function for any given argument. It was the case when it was prime, and then phi of p was just p minus 1. That was this top line here. But there are these kind of standout points that have a relatively low phi value. See, this is something up around 800 and something, but it's still got quite a low phi value compared to the majority of things around 800. And, well, we haven't proved anything which is very clear about which integers these are that give these very low, relatively low phi values. So how do you know if we're looking for the solutions phi of n equals 12? Okay, they're probably all around this range here. 12 is about here, my finger is. Across here, so they're probably all bunched here, but you do get these low down points. How do you know? Are you confident that you could never get one of these falling down below and hitting phi of n equals 12 again? I mean, it looks unlikely. If you continue to graph out, you'll see it roughly as a kind of expanding fan like that. You do get these values that are kind of low all the time. So we could never be 100% sure that we've found all the solutions. So maybe we'll go. So, you can see here. This is the list of all the phi values. You can see a few 12s here. Okay, we could just go and pick those out. But let's try and argue straight from those two facts we know about the product formula and the fact that phi is multiplicative. Maybe we can arrive at the solutions, find the solutions, and hopefully prove that our solution set is complete. There are no other ones. Then we can check with the computer to check and see if we found the correct ones. Or what the hell is that? So let me change for n in the range 1 to 1000 if Euler phi n equals 12. Just what I want to see. Tuple of the n value. Okay, so we seem to see, so the solutions that we can find computationally are 13, 21, 26, 28, 36, and 42. They all have a phi value of 12. So let's see if we can go and prove that there aren't any other ones. Try and set up the problem generally and approach it with the product formula and the multiplicative problem. Okay. So we begin this. So at the moment, we don't know what the n's are. Wondering how might n be a solution to this. Well, if n has a factorization, if we don't know anything about n to begin with, we have to allow it to have a completely general form for prime factorization. So this is how we've normally been writing this. It's a product of powers of primes pi, and there's r primes in the product, and they each appear to exponent alpha r. Okay? That's completely general. That could be any integer at all. Then the product formula says that phi of n is equal to a product over the same range, and you've got similar powers of the primes, except the exponent is one less, and you've got these extra factors here. Now, if this is equal to 12, we ask ourselves what restrictions on the pi does it give? At the beginning, we don't know what n is, so there's no restrictions at all on what prime numbers and how many of them you can allow in here. But if you start to say, well, hang on, this phi of n value has to be 12. So this expression here has to be 12. What restrictions does that place on? Well, 12 is, as a factorization, 12 is 2 squared times 3. 2 squared times 3, and it has factors. And it has factors. The factors of 12 are 1, 2, 3, 4, 6, and 12 itself. It has all of those factors. Just considering, in fact, all the factors of 12, we can get a fairly heavy restriction on the possibilities for the primes pi. So we might see the primes. Well, we might see 2. 2, 3. Remember, if a prime appears as a factor in the prime factorization of n, you're going to get one less power of that prime here, and you're going to get one less than the prime here. So if you have a prime 2, that will generate some 2's and a 1. Well, 2's and 1 are factors of 12. If you had a 3 appearing up here, forgetting for the moment, considering what the exponents might be. But if you did have a 3 up here, you get some 3's here and a 2 here. Well, 3's and 2's and 6's are factors of 12, so we shouldn't rule that out. 4 is in the prime. 5 is the next prime. Well, we should admit the possibility that 5 is appearing up here. It would generate some 5's. Now, 5 isn't a factor of 12, so we'd have to ensure that we only had 5 to the power 1 up here. But then this part would generate a 4. But 4 is a factor of 12, so we shouldn't rule it out that 5 could occur. We should allow in the prime 7 as well, because 7 would generate a 6 here, and 6 is a factor of 12. Again, we wouldn't want any 7's to survive here, because 7 is not a factor of 12. So we should only allow 7 to the maximum power of 1. What other primes are there? Not 8, not 9, not 10, 11. Can there be any 11's in the prime factorization of n? No, why not?
Well, if you reduce it like you've just done with 7 and 5, you get 10, but it's not a factor.
You'd get 10. If there were some 11's up here, a 10 would appear here, which would have a 5 in it, and 5 is not a factor of 12. Yeah. So it can't be 11. Any other primes? One more prime that we should consider. 13. Yeah. Because while we wouldn't want any 13's to survive down here, so we'd only allow it in with a maximum power of 1. But then this factor would generate a 12, but that doesn't cause any problems because 12 is a factor of 12. But certainly there should be no higher primes allowed in. Because if you do, for instance, if you allowed in, what's the next prime, 14, 15, 17. If we allowed in 17, that would generate a 16 here. Yeah, and 16 is not a factor of 12. So we'd make the phi value too big. Yeah, make the phi value too big. So those primes don't obviously break any rules about allowing them in. Maybe some of them we've already seen, they can only appear to a maximum power 1. But we should entertain the possibility that those primes are appearing in the time factorization then. So we might see the primes here in N, but certainly no other ones, no others. As for all other primes P, the P minus 1 factor that you get here is going to be strictly bigger than 12. Okay? So you can't have it here as one of the factors in a product, which is supposed to equal 12. It gets bigger than 12. So what that means is remember, we're trying to find solutions to 5n equals 12. When we introduced n at the top, it was completely general, any prime factorization at all, but now it's heavily restricted. Okay. So any solutions n must be of the form n equals 2 by a 3 by a 5 by a 7 by a 13, and these might have some exponents on them. And I'll just write A, B, C, D, E for the exponents. Now we've already, from our talk there above, considering that 12, its prime factorization is 2 squared by 3. The A can be no bigger than 3. So if the A was 4, then you'd have a 2 to the 3. You'd have an 8 in the product for 5. Then the 3 can be no bigger than 2. So the B must be less than or equal to 2. The C must be less than or equal to 1, and the D must be less than or equal to 1, and the E must be less than or equal to 1. So in other words, C, D, and E can only either be 0 or 1. If they were any higher, if we had 5 squared here, then there'd still be a 5 in the product for phi of n, and there isn't a factor of 5 and 12. So 5, 7, and 13 can, at worst, or at best, only appear to the power 1, but the 2 and the 3 could maybe appear to higher powers. So the first case would be, so investigate the possible cases. We'll work from the largest one down. Suppose the 13 was here. Okay, suppose E was equal to 1. Then what we'd be saying is, i.e., we'd be writing n as 13 times n. So we'll just bundle up all the other stuff in n as n. I won't have to address it directly here, I don't think. That would imply that the value of phi of n would be phi of 13 times m. But of course, m and 13 are co-prime. 13 does not divide n. So that implies that phi of n is equal to 12 times phi of n. And if this is equal to 12, remember this is the equation we're trying to solve, well, this implies that phi of n has to take the value 1. And there's only one number which has phi value, well, sorry, 2. 2 numbers which have phi value equal to 1. Okay. And that is m equal to 1 itself times 2. Okay. You just consider the original definition, counting the number of numbers that are co-prime to the top number. Every other argument m will have a higher phi value. So if there is a 13, then the m could be 1 or 2. And that would give us solutions to 5n equals 12. So that implies n equals 13 and 26 are solutions. Well, that's the case if e was 1. So now we found some solutions. So now we can assume that e is 0. So there are no 13s. So here on, assume e is 0. We've already found the solutions for e equals 1. Now let's assume that d is equal to 1. So that's the case. I.e., I'm going to say n is equal to 7 times n. Okay, so I can factorize a factor of 7 out. Well, as before, that's going to imply that phi of n is phi of 7 times phi of m, which is equal to 6 times phi of m. And if this is equal to 12, that has to imply then that the phi of m is 2. 6 times 2 is 12. Okay. And if you interrogate the product formula for phi, you'll see the only solutions to phi of m equals 2 are, well, there's a few of them, m equals 3, 4, and 6. 3, 4, and 6. 3 is prime 3, 5, 3 is 2, 4 is 2 squared, so 5, 4 is 2, 6 is 2 times 3, so 5, 2 times 3 will be 2 as well. And there are no other solutions. Okay? So these very low values, 5m equals 1 or 5m equals 2, you can figure out those solutions just from looking at the product formula exactly. Product formula directly. So if there is a 7 in the factorization of n, we can have the values 3, 4, and 6 for the other factor. So that gives the solutions. It implies 21, 28, and 6 times 7 is 42 are solutions. Yes, that's good. We found 5 solutions so far: 13, 26, 21, 28, and 42. We just continue like this. So that deals with the case when d equals 1. So here on assume d is 0.
Oh.
So now we're just considering n's as maybe 2 times 3 times 5 to some powers. And so assume now that c is equal to 1. C was the power on 5. So n is equal to 5 times n. That will imply phi of n is phi of 5 times phi of n. So phi of n will be co-prime. That implies phi of n is 4 times phi of n. And if this is equal to 12, that will imply phi of m is equal to 3. But considering the product formula, for phi, we never have phi of m equals 3. Never have phi of m equals 3. And that's justification. Have I got the?
Yeah, I do have it.
if you look at the need much justification for that. If we look at the product formula there again, how could this thing equal 3? Well, it can only come about. I mean, how could you end up with a 3 here? Well, you could certainly end up with a 3 here if there was 3 to at least a 3 squared here. If there was at least a 3 squared in the prime factorization of n, then you'd end up with a 3 here. Then you'd also end up with an extra factor, 2. 3 minus 1 is 2. Okay? So you'd have 2 by 3, you'd already have a 6 here, so that couldn't be equal to 3. The only other way you could get 5n equals 3 is if the 3 somehow came from this. So if there was a factor of 3 in this, but then it would have to come from a high prime, a prime beyond 2, one of the higher primes, in which case this factor would be even. There might be a 3 in it, but it would also be even. In which case, it could never equal 3. So there's just no way for this expression to equal 3. There's no way to generate just a factor of 3 here without bringing in other factors as well. So if c is equal to 1, if there is a factor of 5 in n, which would generate a 4 in the value of 5n, which might be sitting here and give a value of 12, it just can't, because the other factor of 3 here would have to come from a 5n, and that can never happen. Never have 5n. So there are no solutions here. There are no solutions to 5n equals 12 here. So here on assume c is 0, i.e. n is equal. I think we can do these all in one go now. So if we've dealt with the 13, 7s, 5s, we've just got 2s and 3s. Let's just say, and we can tackle this directly now, because that implies phi of n is 2 to the a minus 1 times 3 to the b minus 1 times a 2, another 2, so it's 2 to the a times 3 to the b minus 1. And if this is equal to 12, well, there's one and only one way that can be equal to 12. Okay, because 12, this is a prime factorization. A load of 2's times a load of 3's. And 12 factorizes as primes as 2 squared times 3. So the only way this can happen is if, remember, prime factorizations are unique. The only way this can happen is if a is 2 and b is 2. That implies a is 2, b minus 1 must be 1, so b must be equal to 2. I.e., one final solution, which is n equal to 2 squared times 3 squared, 4 by 9, 36. Did I have 36 before?
No.
No. So all the solutions, and this is a proof now, this is a complete set of all the solutions to 5n equals 12. We have 13, 26, those are the first two. Then we have 21, 28, 42, nothing for 5s, and then this last one, 36. So 1, 2, 3, 4, 5, 6. Just those 6 solutions. Hopefully I haven't missed it. So those are certainly all solutions, and we're confident that they are all the solutions because we had to exclude every other prime apart from that, those 2, 3, 5, 7, 13 that we considered at the start. Because any other prime would generate a factor bigger than 12 in the expression 5n, so you can never have that equal to 12. Splash back to the computer, just check. Those were all our solutions here. 1, 2, 3, 4, 5, 6. Yeah. 13, 21, 26, 28, 36, and 42. Okay. So there's a few values down here that give 5n equals 12, and then there's no more. Okay. It's easy to match that with the look of the graph, but we've fully proved it. Okay. And again, you're seeing at play the product formula and the multiplicative property of phi. So they're the very important key facts of phi. Okay, I'll leave that there for now. See you next door in a minute or two.
Wait, where's the